Welcome to Lecture 3, the Tool Calling Agent. In Module 2, we ship the infrastructure. Now we build the agent itself, and we do it with one architectural pattern that changes everything: Model Context Protocol. The premise: in the old world, every tool a Claude agent could call lived inside the agent process. The agent image needed Unity Catalog client libraries, S3 credentials, Qdrant client libraries, the embedding model client. Every tool dependency added image size, attack surface, and another reason for a CVE patch to force a redeploy of the whole agent. In the new world we'll see in the next slide, tools are standalone Kubernetes services. The agent has 0 tool dependencies in its image. It discovers them at boot over HTTP. You'll see how that single shift simplifies your deployment, your security model, and your scaling story. And in the closing slide, you'll see the agent in action, fully traced, with tool spans visible in MLflow. This is the slide that explains why MCP matters. One process becomes 3. Look at the diagram. The agent service version 0.2.0 only knows about the multi-server MCP client and a list of URLs. To its right, 2 MCP servers. Each is a small, fast MCP service exposing tools over streamable HTTP on port 8080. The first one, MCP UC tools. It owns the structured data tools, get service history, and get return policy. It connects out to Unity Catalog and to MinIO. The agent has no idea what UC or S3 even are. The second one, MCP Vector Tools. It owns the Vector Search tool, Search Product Docs. It connects out to TEI for embeddings and Qdrant for similarity search. Again, the agent has no clue. 3 benefits. First, each MCP server owns its own credentials. Rotating an S3 key now affects exactly one pod, not the entire agent fleet. Second, the agent image dropped a long list of heavy dependencies. UC client, S3 client, Qdrant client, embedding client, all gone. Smaller image, faster builds, fewer CVEs. Third, you can scale, version, or swap any tool service independently of the agent. That's the pattern. Now let's see it live. One line of setup gets you full observability. In the agent's startup code, we call MLflow.langchain.autolog. That single call registers callbacks with LangChain's tracing infrastructure. From that moment, every LLM call, every tool invocation, every intermediate graph state is captured into MLflow. Look at the trace. A run ID, a duration of 2.4 seconds, 3 spans. The model is Claude Sonnet, status OK. Below a Gantt chart timeline, you see the top-level chain span, langgraph.invoke. Inside it, 2 LLM spans for 2 chat OpenAI round trips through Light LLM, plus 1 tool span for the search product docs invocation in the middle. Each span shows token counts, latency, and the exact tool call arguments and results. At the bottom, the final output text. Cleaning instructions for an XR200 stroller with a citation back to the source document and its similarity score. This trace is your debugger when an agent gives a wrong answer. You can replay any production interaction, see which tool returned what data, see which prompt produced which choice. No print statements, no custom logging, just one line, and you have a complete audit trail. That wraps Module 3. In Module 4, we go deep on the data side, turning raw documents into sub-100 millisecond vector search with Qdrant. See you there.